Good day. The topic is the fundamental properties of fluids. For the introductory part, let us define engineering mechanics as the study of state of body at rest or under equilibrium or motion under action of forces. For the branches of engineering mechanics, it is divided into two. First, the mechanics of fluids, which is our course, and the other one is the mechanics of solids, under which your other subjects, such as the statics and dynamics for mechanics of rigid bodies, and strength of materials, that is the mechanics of deformable bodies. For fluid mechanics, it is the branch of engineering mechanics concerned with fluids at rest or in motion. Fluids are under phase of matter capable of flowing, having particles which easily move and change their relative position without a separation of the mass. And phases of matter under fluids are first the liquid. So we have now for liquid free surface. A given mass occupies a given volume in a container and practically incompressible. On the other hand, for gas, it does not have a free surface. A given mass occupies all portions of any container regardless of its size, and it is compressible. So for the two systems of units, first is the SI or International System, more popular as metric system. Sample units are meter, kilogram, and Newton. For the second, it is the Imperial and United States or US customary units, or more popular as the English system. Sample units are inch, foot, slug, or pound. And note that for this course, we will consider water as the reference fluid because it is considered as the universal solvent. And some properties of water are, so it is colorless, transparent, odorless, liquid. So for the properties of fluids, so let us now consider these properties as the unique attributes, qualities, or characteristics of the fluids. So first is the mass density, or Greek letter rho, defined as the equivalent mass of a fluid per unit volume. In formula, rho is equal to m all over v, where rho is the density in kilograms per cubic meter or slug per cubic foot. M is the mass quantity of matter present in an object. And take note that for mass, it is constant regardless of where it is located. And the units are either in kilogram or slug. And for V, we will consider the volume as the amount of space occupied by the substance in cubic meter or cubic foot. So the standard values for water are 1,000 kilograms per cubic meter if it is in metric, 1.94 slug per cubic foot if that is in English. Second is the specific weight or unit weight, represented with Greek letter gamma, defined as the equivalent weight of a fluid per unit volume. In formula, gamma is equal to W all over V, where gamma is the unit weight in newtons or kilonewtons per cubic meter or pounds per cubic foot. W is the weight and it is the force due to gravitational pull. it is either in newtons or pounds. And for W, W is equal to the mass times the gravity, wherein G is the gravitational acceleration, 9.81 meters per square second in metric, or 32.2 feet per square second for English. And again, V is the volume in cubic meter or cubic foot. And if we will now substitute the equation of W or weight, so the relationship of the unit weight and density is rho times G. And note that for water, the standard value for unit weight are, so 9.81 kilonewtons per cubic meter in metric, or 62.4 pounds per cubic foot in English. Third property is the specific gravity, or small letter s, defined as the ratio of the density, or we may use unit weight of a substance to the density or the unit weight of a standard or reference fluid. So usually water for a liquid or solid, and air for a gas. So in formula for liquid, S is equal to rho of the liquid or gamma of the liquid over the rho of water or gamma of water. For gas, S is equal to rho of gas over rho of air or gamma of gas over gamma of air. And take note for the following now, the water, S is equal to 1, and for mercury, S is equal to 13.6. So the fourth property is the specific volume or V sub S, defined as the equivalent volume of a fluid per unit mass. In formula, V sub S is equal to V all over M, where V sub S is the specific volume with a unit cubic meter per kilogram or cubic foot per slug. V again is the volume, and M rather is the mass. So let us now take our first sample problem. For problem number 1, a given liquid has a mass of 3,100 kilograms and a volume of 1.23 cubic meter. So determine the weight, mass density, unit weight, and specific gravity. So for weight, W is equal to M times G, wherein M is 3,100 kilograms and G for metric is 9.81 meters per square second, or that is 30,411 newtons or 30.411 kilonewtons. For density or rho is equal to M all over V, wherein the mass is 3,100 kilograms over the volume that is 1.23 cubic meter. And therefore, our density is 2,520.325 kilograms per cubic meter. And for the unit weight, we will consider two methods. First is the standard formula, that is gamma equal to W all over V, wherein W taken now from letter A requirement, that is 30.411 kilonewtons over the volume that is 1.23 cubic meter, or gamma is 24.724 kilonewtons per cubic meter. On the other hand, for our method number 2, we will consider the relationship of gamma and rho. That is, gamma is equal to rho times G. And rho from letter B requirement is 2,520.325 kilograms per cubic meter, multiplied to G, that is 9.81 meters per square second. Thus, for gamma, that is 24,724.39 in newtons per cubic meter, dividing it with 1,000 for it to be converted to kilonewtons. Thus, the value of gamma is 24.724 kilonewtons per cubic meter. For the specific gravity, we will as well consider two methods. For method number 1, we will consider the values of density. Thus, S is equal to rho of the liquid over the rho of water, or that is 2520.325 over the standard rho of reference fluid, which is water, that is 1000. Cancel out all the units. S is equal to 2.52. While for method number 2, we will now consider the values of the unit weight. So for the unit weight of the liquid, that is 24.724 kilonewtons per cubic meter, while the reference unit weight of water, that is 9.81 kilonewtons per cubic meter. And cancel out all the units. S is equal to 2.52. Next, for sample problem number 2. A bottle of water weighs about 10.95 newtons on Earth. For A, compute mass in kilograms. For B, determine the mass of water in kilograms if it will be placed on a planet with gravitational acceleration of 8.5 meters per square second. So first, the mass of water on Earth. So W again is equal to M times G. Rearranging this to define M is equal to W all over G, wherein W is 10.95 newtons over the gravitational pull for metric on Earth is 9.81 meters per square second. Mass therefore is equal to 1.16 kilograms. Next, how about if we will now be placing this substance on a planet with G that is equal to 8.5 meters per square second. Do we need to consider the weight on Earth then to be divided with this value of G that is 8.5 meters per square second? So for the answer, again, as defined for M is constant regardless of what is the location, where is that substance located or position. Therefore, M as constant, same as letter A, M is still 1.16 kilograms. So even though we will place this specific volume of our substance in another planet or another location, the mass will still be 1.16. So if we will now be comparing mass and weight, mass is dependent on the component of its matter, while for the weight, it is dependent on the force exerted by this matter with respect to the gravitational pull. Thus, W is dependent on G, while M is constant. So let us consider the fifth property. So the dynamic viscosity, or represented with Greek letter mu, defined as the measure of a fluid's resistance to deformation under shear stress. In formula, mu is equal to tau over small v over t, where mu is the viscosity with units Pascal second or pound second per square foot. Tau, on the other hand, is the shearing stress in Pascal or PSF. And shear stress or tau is equal to F, the shearing force, over A, the shear area. And the small v is equal to velocity, and small t is the thickness of the considered fluid. For the sixth, the kinematic viscosity, represented with Greek letter nu, defined as the ratio of dynamic viscosity with density. in formula, nu is equal to mu all over rho, where nu is the kinematic viscosity in square meter per second or square foot per second. Mu is the viscosity in Pascal second or pound second per square foot, and rho as the density in kilograms per cubic meter or slug per cubic foot. So for our next sample problem, a block slides down in an inclined plane 20 degrees on 3 millimeter thick film of kerosene with viscosity of 0.093 Pascal second. If the contact area is 0.25 square meter and weight of the block is 20 kilograms, determine the velocity of the block and kinematic viscosity of the fluid. Assume that the specific gravity of the kerosene is 0.7. To start, let us solve first the weight of the block since the problem stated only the value of its mass. Thus, W is equal to mass times gravity, where mass is 20 kilograms and the gravitational pull is 9.81 meters per square second. Therefore, the value of weight is 196.2 newtons. Knowing this value of W, let us now determine the shear force acting now in between our sample block that slides now through the kerosene. So what is this F between the kerosene or the interface of kerosene and the block? So consider the FBD or the free body diagram of the block. Again, it is acted upon with its internal force, that is the self weight, and externally with this force F, the shear force F, which acts as the counteracting force. So the summation now of the forces along our rotated axis x equal to 0, F is equal to the W sub x, which is the component of our weight in terms of the rotated axis x. And taking now, for us to define what is this value of W sub x, the force triangle of the weight W with respect to Wx and Wy. So for Wx, it is now equal to the W sine of 20 degrees since Wx is the opposite side for this angle that is 20 degrees or the angle of the incline. And if we will now substitute the weight value that is 196.2 newtons, the value of W sub x is 67.104 newtons. And therefore, since the summation of forces along x specified that F is equal to this Wx, F is equal to 67.104 newtons. Using now this F for velocity, using the equation that is mu equal to tau all over V over T, rearrange, thus the equation for V is equal to tau sub tau multiplied with thickness T over the value of viscosity mu. Or for tau again, that is equal to the shear force all over the shearing area, then multiply that with T over the mu. For F, that is 67.104 newtons over the shear area, which is 0.25 square meter, multiplied to the thickness of the kerosene, that is 0.003 meter, over the mu, that is 0.093 newton per square meter second. Thus, the value of velocity is 8.659 meters per second. So for kinematic viscosity or nu, using the equation nu equal to mu over rho. Determine first the density of the kerosene using specific gravity equal to rho of kerosene all over rho of water. Cross multiply this rho of water, the rho of or the density of kerosene is equal to the specific gravity of kerosene, that is 0.7 multiplied to the rho of water. Standard value in metric is 1,000 kilograms per cubic meter. Thus, rho is equal to 700 kilograms per cubic meter. And for nu is equal to mu over rho. Thus, mu as given is 0.093 in newtons per square meter second over rho, that is 700 kilograms per cubic meter. And if we will expand the unit newton in kilograms meter per square second and cancel out all the units, we will now have the value of the nu or kinematic viscosity as 1.329 times 10 raised to negative 4 square meter per second. So let us continue with the discussion of properties. So for the seventh, the surface tension, or Greek letter sigma, defined as the material property whereby a liquid at a material interface, usually liquid to gas, exerts a force per unit length along the surface. So it is responsible for molecular attraction. So as you notice, the surface of the liquid, that is the portion in which surface tension apply. Okay, so in formula, H is equal to 4 times sigma times cosine theta all over gamma times D, where H is the capillary head in meter or foot, sigma is the surface tension in Newton per meter or pound per foot, theta is the contact angle in degrees. So for water to glass interface, the value of theta is 0, while for mercury to glass, that is 140 degrees. Gamma is the unit weight, and D is the diameter of the tube. So the two possible conditions are, first, the capillary rise or the surface of fluid inside the tube is higher than the original surface. And the other is capillary depression or drop, or the surface of liquid inside the tube is lower than the original surface. An example for the capillary depression would be the viscous fluids such as honey. So if you will consider now a very, very thin tube, insert that to honey. So there is a difficulty for honey to flow through this very, very thin tube. Thus, it will now consider a capillary drop or a decrease in its elevation or surface with respect to the original surface. So for our sample problem, under the capillarity or the surface tension. So for this problem, estimate the height to which the liquid will rise or drop in a glass tube of diameter 25 millimeters. For A, water with sigma equal to 0.073 Newton per meter. And for B, mercury with sigma equal to 0.52 Newton meter. So for water, the capillary head H, so theta for water to glass tube, theta is equal to 0. Thus, H is equal to 4 times the sigma, that is 0.073 Newton per meter, multiplied to cosine of theta, that is 0, over the gamma of water. So for us to have a consistent unit, we will now consider gamma of water as 9,810 which is in newtons per cubic meter. So multiply this to the diameter of the tube, that is 0.025 meter. So for H now, it is equal to a positive 1.191 times 10 raised to negative 3 meter. Positive, which means that it is a capillary rise. The elevation inside the tube is higher than that of the original elevation. Thus, rewriting our answer, H is equal to 1.191 in millimeters already, so which is a capillary rise. So for letter B, we will consider now mercury, capillary head, H. So the theta for mercury to glass tube is equal to 140 degrees. So determine first the unit weight of mercury. So gamma mercury, using now the specific gravity of mercury equal to gamma of mercury over gamma of water. Cross multiply or rearrange, we have now the gamma of mercury equal to the specific gravity of mercury multiplied to the unit weight of the reference fluid, that is water. For the specific gravity of mercury as standard, so that is 13.6 multiplied to gamma of water. So for consistency, we will consider 9,810 in newtons per cubic meter. Thus, the value of the gamma of mercury is 133,416 newtons per cubic meter. Substitute in our equation, we have now 4 times the sigma of 0.52 Newton per meter multiplied to the cosine of the angle 140 degrees over the gamma of mercury, that is 133,416 newtons per cubic meter multiplied to the diameter, that is 0.025 meter. Thus, H for mercury is negative 4.777 times 10 raised to negative 4 meter. Negative means it is a capillary drop or depression. And if we will multiply this with 1,000 for it to be converted to millimeters, our final answer H is 0.477 millimeter, and replace negative sign as capillary drop. So please omit the sign if you intend to indicate that the height H is a capillary drop. So the negative sign indicates only the direction of the measurement. Negative means it is downward. So for the eighth property, the compressibility, or Greek letter beta or beta. So defined as a measure of the relative volume change of a fluid as a response to a pressure change. So if we intend to apply a confining pressure, what will happen to our fluid? Ideally speaking, liquids are incompressible, while gases are compressible in nature. But if we will apply a massive value of confining pressure, this liquid will have a minimal value of compression value or compressibility. And in formula, beta or beta is equal to the negative dV, or the differential volume, all over the initial volume over dP, or the differential pressure, wherein dV is the final minus the initial value and dP is the final minus the initial pressure value. On the other hand, for the ninth property, the bulk modulus of elasticity, or E, capital E sub B, defined as the property that relates changes in pressure to changes in volume. For example, expansion or contraction. Similarly, with compressibility now. If we apply pressure, is your fluid elastic or capable of changing its volume? So in equation, the E sub B is equal to the negative of the change in pressure over the change in volume per initial volume. Or since this is the reciprocal of the compressibility, we may determine E sub B as 1 all over beta. Again, E sub B is the bulk modulus of elasticity with the unit PA or pascals or PSF pounds per square foot. dV again is the final minus initial volume. V is the initial volume and dP is the final minus the initial pressure. So for the sample problem under the group of compressibility and bulk modulus of elasticity, a water compressed in a container at a pressure of 1 megapascal has a volume of 0.98 liter. And if the pressure is increased to 3 megapascals, the volume become 0.83 liter. Determine the bulk modulus of elasticity of the liquid and its compressibility value. So for letter A, the bulk modulus of elasticity or E sub B is equal to the negative dP all over dV all over V. So the negative will counteract the negative value for the decrease in volume because again, if we intend to compress our fluid, what will happen to the volume? It will now decrease. So therefore, the value of dV will consider a negative value. So for this E sub B, it is now equal to the negative of, so dP is the final pressure minus the initial pressure over for dV, that is the final volume minus the initial volume, so per initial volume, or that is negative, so 3 minus 1 in megapascal over the quantity, so 0.83 the final minus 0.98 the initial in liter over the initial, that is 0.98 liter. Thus cancel out the unit of volume that is in liter. E sub B is equal to 13.067 megapascals. On the other hand, for compressibility, let us consider two methods. First method is the standard formula, that is beta is equal to the negative dV all over V over dP. Again, consider the difference of final and initial. It is now equal to the negative, the quantity 0.83 minus 0.98 in liter over 0.98 liter over PF, that is 3 minus PI, that is 1. And since we are dealing with compressibility, let us now consider mega as times 10 raised to 6 Pascal. Thus, beta is equal, or compressibility is equal to 7.653 times 10 raised to negative 8 in square meter per Newton. So again, the liquid is ideally incompressible. Thus, the value of beta is very, very, very low. On the other hand, for method number 2, let us now consider the relationship of beta and bulk modulus of elasticity. So reciprocal of the other. Thus, beta is equal to 1 all over E sub B, or that is 1 all over 13.067. So mega will be converted as times 10 raised to 6 Pascal, or that is 7.653 times 10 raised to negative 8 square meter per Newton. So for the 10th property, the celerity of pressure waves, or small letter C. So other term is pressure disturbances, and defined as in a fluid medium, gas or liquid, is used as a relative measure for the speed of an object moving through the medium. So for celerity for rigid pipe, C is equal to the root of E sub B over the rho or density. While if we are dealing with a non-rigid pipe, C is equal to the root of E effective, or otherwise E effective may be called as the composite bulk modulus of elasticity. So over again the rho. So C as the celerity of pressure waves will consider same unit as velocity, that is in meter per second or feet or foot per second. Rho again is the density, EB is the bulk modulus of elasticity, E sub F is the effective bulk modulus of elasticity, or again, other term for this EF is the composite bulk modulus of elasticity. So with units Pascal or PS F. And for E sub F, it is equal to E sub W or the bulk modulus of elasticity of water over 1 plus D, the diameter of the pipe, times E sub W over T, the thickness of the pipe wall, times EP, the bulk modulus of elasticity of the non-rigid pipe. On the other hand, relating to the 10th property, we will consider water hammer pressure or small letter P sub B. So it is the pressure due to closure of the valve. Or as you notice, if you have a valve that is uh, fully open with aggressive flow and suddenly you will close that valve, so the activity inside now the valve is a water hammer pressure. So for us to define this water hammer pressure, P sub B is equal to rho times V times C. Again, rho is the density, V is the velocity of the flow, and C is the celerity of pressure waves. On the other hand, so for us to have this water hammer pressure, for the instantaneous closure, C is equal to 2 times L all over T sub C, wherein L is the distance traveled and T sub C is the time of closure. So let us now consider problem 6 under our celerity of pressure wave. So for this problem, water flows at a rate of 2 meters per second in a 2.5 kilometers long, 600 millimeters non-rigid pipe that is 20 millimeters thick. Bulk modulus of elasticity of water is 2.2 times 10 raised to 9 pascals. Bulk modulus of elasticity of the pipe material, again non-rigid pipe, is 1.4 times 10 raised to 11 pascals. And density of water is 998 kilograms per cubic meter. So as you notice, this is below the standard, which is 1,000 kilograms per cubic meter. So some of the properties, if ever that we increase temperature, so the values will tend to decrease. While if we increase the temperature, or decrease the temperature rather, the possibility for our property values will increase. So such as an example, if you will consider now the heating process of air, so what will happen? The air will become lighter. Thus, it will now be considered as the primary component for a hot air balloon to help this or help it fly. Okay, so if we will go back to the example, so for the requirements, determine for letter A, the composite bulk modulus of elasticity, for B, the value of celerity of pressure wave, for C, the max time of closure that can be considered as the instantaneous closure if the valve at the end is closed. And for D, the hammer pressure due to instantaneous closure. So for letter A, that is the composite bulk modulus of elasticity, again, other term for the effective bulk modulus of elasticity. So the EF is equal to E sub W, that is 2.2 times 10 raised to 9 pascals over 1 plus D. So we are not required to convert the diameter and thickness since the units will be disregarded. So again, D is 600 millimeters multiplied to EW, that is 2.2 times 10 raised to 9 pascals over T, that is 20 millimeters multiplied to the elasticity of the non-rigid pipe, that is 1.4 times 10 raised to 11 pascals. Or the E effective is equal to 1,495,145,631 pascals. On the other hand, for the celerity of pressure wave C, since this is under non-rigid pipe, C is equal to the root of the E effective all over the rho. So E effective again is 1,495,145,631. So we will consider already the expanded unit, that is kilogram meter per square second per square meter over the density, that is 998 kilograms per cubic meter. So for the value of the celerity C, it is equal to 1,223.986 meters per second. And for the instantaneous time of closure, or T sub C. So modifying our equation, the T sub C is equal to 2 times L all over C. So 2 times the total distance traveled, so from the valve towards the source and back. So we will consider 2,500 meters. So twice of that L all over C, that is 1,223.986 meters per second. So cancel out the unit of distance, that is meters, leaving us T sub C, that is 4.085 in seconds. And finally, for the hammer pressure due to this instantaneous closure, P sub B is equal to rho times V times C. Rho, that is 998, V, that is 2, C, that is 1,223.986 meters per second. So if we will consider the unit, that is kilogram meter per square second, that is already in newtons. So cancel out 1 meter. Therefore, for the denominator, so the remaining unit is square meter. Thus, we will consider Newton per square meter, or that is in pascals. Thus, for P sub B, if we will now consider this value, that is 2,443,000 or 76, then 0.208 pascals. And if we will consider now times 10 raised to 6, that is now 2.443, replacing times 10 raised to 6 with mega, then the answer is in mega pascals. Or P sub B again is 2.443 mega pascals. Okay, so that's it for the properties of fluids. Take care and God bless.